Okay, guys. Next week, November 22nd, we'll have our quiz, which will cover handout 8 to 11 as per our course handout outline. Let me share it with you. So can you see the outline? So it's here. So 8, 9, 10, and 11. Today we'll take 10 and 11 because they are connected to each other. 8 and 9, we took it last week. And next week, we will cover the last handout at 12. It's already in OWL with the code. I asked you last week to run the code of 8 and 9. And if you have a question, we can have the examples again this week class. The topic for today, it's about complexity of the program. Both handout 10 and 11 are talking about the same topic, which is the program efficiency. So how to write high quality code. So as you see here, November 22nd is the day of quiz 2. And it will cover handout 8. We call it week, but it's a handout 8, 9, 10, and 11. It will be in the same manner as quiz 1 and midterm. By the way, the midterm marks are ready. You should, I believe that most of you did very well, guys, in the midterm. Everybody can see his mark and also a feedback where you lose marks. From the beginning, after the quiz, you can see like your mark is 10, 8, 9, which is the multiple choices mark, which is there was I think 10 multiple choices with 10 grades, and we have some short answers also 10 grades. With short answers, I asked the TA to give a detailed comment where you lose marks. So I believe everybody can see it. Also, the project proposals marks also available. The mark you get is based on the proposal as a group work. So all group members got the same mark for their proposal. But I have a question, guys, that in the final report, and in the presentation, I need all of you to add, I will send an announcement, each member contribution. I received some few emails from some groups that some group member, they are not contributing at all. So I want from the group focal point that the group choose who's in touch, the one who submitted, also to submit a report about the contribution. You can say X, Y, and Z, they have equal contribution. This one has less. I leave it, it's one page for with the presentation. When you submit the presentation, should be the last slide. You don't have to present in front of the class, but when you submit in OWL the presentation, please make last slide in your presentation about each member contribution. I know the majority are working very well, but sometimes we have some, like one group member here who's careless, who's not contributing, who's not do his duties. as a group member, please let us know, because the presentation mark will be individual. There is a part for a group, the whole presentation evaluation, and there is a part for individual. And those who did not contribute at all, they will get 0. And please don't allow them to present with you guys, because I cannot stay idle, do nothing, and in the presentation day, I read 1 or 2 slides and get the same mark as those who work hard. It's unfair. So we have to be fair. Is that clear, guys? Is that clear, guys? Now also we'll take votes for, yeah, also tonight or tomorrow, because tomorrow I believe is the deadline for assignment 2. Yeah, it's due tomorrow by the end of the day. So either tomorrow or maximum Wednesday morning. Most probably tomorrow or early, like midnight between Wednesday and Thursday, I will release assignment 3, which is last assignment in this course. And it will be due on, so if we release it tomorrow, which is 17, then I'll make the deadline I'll make the deadline on 28th, which is before your presentation. And it is a simple assignment. It's not a hard assignment. Because based on what I'm seeing, that 24 students already submitted their assignment 2, and more than 30 students, they did not submit yet. And the deadline is tomorrow. So after the deadline, I will release assignment 3, because I don't want you to be mixed or confused between 2 assignments at the same time. And I'll make the deadline by 28. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 days to submit assignment 3. Is that clear, guys?
Yes.
Okay. Also, I received an email from one group who scheduled for November 29th, the first day of presentation of project presentations. They just sent me an email yesterday, late night, asking to be on the December 6th. So if any group willing to present from those who scheduled in December 6th, willing to present on November 29th instead, to be with the first day of presentations. If a group find themselves that they can, because they have certain circumstances with that group, if you find yourself, you are willing as a group to present on the first day, please send me an email and I can replace your group to be on the 29th, and I will move that group to December 6th. Otherwise, they have to present in their scheduled date. So it's optional for those groups. I don't know the groups, the TA pick the time randomly for each group which day to present. So if you find yourself that you are willing to present on the 29th instead of December 6th, you are more than welcome to send me an email telling me that we would prefer to move to the November 29th, then I can move that group back to December 6th and their problem will be solved. Otherwise, they have to present on their day. Also, another comment I would like, because I don't receive any question about this. I clarified this before, but just as a reminder, those groups, even if your report is not done yet, by November 29th, because you have till December 6th, then you can present what the group did till that moment, and tell me that we still need to do 1, 2, 3 in the report. But I would not accept also that you said, oh, we just write the introduction and we do this and we are willing to do that. No, because it's a 1 week, you have enough time to do your project as a group. So I would accept that if 20% left, that would be an acceptable ratio in your presentation, that we done the 1, 2, 3, 4 and still have 5 and 6. I would accept that. Those on December 6th, your topic should be completed, because the second day you just finalize, format your report, and you have to submit in the next day. Is that clear also?
Yes.
Okay, sounds great. So, any question about handout 8 and 9? Anything is unclear? Okay, if there is no question, I'll show some few examples from the handout that we have. Also, as I told you, practice, practice, practice. You have to run the code with Python tutorial or by using Jupyter's, and the code files are available in OWL. You can run them and see the differences, or you can copy and paste to the Python tutorial or with Jupyter or whatever the platform you would like to have. And then you will see the clear. If there is something uncertain for you, you can send me an email, excluding the weekends. So if you want to send an email asking about something, you have till Friday within working hours. So we can arrange for a small meeting to explain the thing that is unclear for you. Our quiz will start at 4 p.m. next Monday. It is for 30 minutes, which is more than enough. I will repeat, all people or all students that need accommodation or more time, it is considered, because I designed the quizzes and exams to have more than enough time to answer all the questions. So the accommodation is considered. I give almost, like, the quiz need 15 minutes. And normally, even with the exam, more than half of the class, they finish their midterm before 30 minutes of the exam. Even I gave 1 hour. Last quiz also, I give 30 minutes. Most than like 70% to 80% of the class, they finish within the first 15 to 20 minutes. So the accommodation is considered. It will be 5 question multiple choices and 5 question short answers, same as usual. And it's worth 10 marks of your total course mark. Do you have any inquiry, anything before I start, guys? Okay. Let me share my screen. Okay, can you see the Jupyter screen? Yes or no? Okay, good. So here, the first example that we started last class about the class coordinate, a coordinate made up of X and Y value. So we use the init self X and Y to initiate the class, self.x equal X, self.y equal Y, and also return a string representation of a self, return between brackets the X and Y values separated by a comma. Then the distance, we define the distance, which is the square root of X is a square divided by Y squares. Then we return them. That distance law in mathematics between 2 points in the coordinate. So we define the object C from the coordinate class. It's an instance of that class. Origin, which giving the coordinate. Also another instance, we call it origin, or another object, we call it origin, which is the original point which with coordinates 0, 0 for X and Y. Then we said print CX origin X. So the C, it is 3, the value of X, and for origin, it is 0. Then print C distance with the origin, it is 5. Print coordinate distance C origin, another way we use it to print the distance, it's also give me 5. Origin distance C, we put the origin at the beginning, it is 5. Then print C, and here we use the string, which is return string representation, like between less than, then a string which contain, we convert the coordinate X of self of the C to X, the value of X, which is 3, then the Y, which is 4, and we put it in this format. So this is the first example that we took. The second example we talk about, which is the class fraction, and we make the init, which is initiate the class string, which returns the representation as we ask it to do. Then we define some operation like add, sub, float, inverse, and inverse will return it to the floating number. And we said at the beginning, we took the fraction, we said 1 and 4, then B fraction 3 and 4. Then we said C equal A plus B. C is a fraction object also. So we print C, which is 16 over 16, print float C, print the fraction, which is 1, 16 over 16, print the float B inverse, which is 3, the inverse of it's 1.33, which is 4 over 3. Then this one, it will give me an assertion error if we send the fraction with 3.4, and we mention why it's error in the handout. Also this one, we said print A times B, it will be also error because multiplied to fraction object, we did not define that. We did not define the operation of multiplication. So this was our second example. Then our third example about integer set, and we add insert, we define the insert, we add the number 3, 4, and 5, then we print it. At the beginning, we print S, which is empty, then we add 3, 4, 3, then we print S, then we add member 3, 5, 6, and then we print S again. So we empty 3, 4, 3, 4, 6, print S dot remove 3, then print S after the remove. After the remove, we print S, then we print 4 and 6. So all details, what each command will do, it was clarified in the previous handout. So these are example of running the code. Also, the last one, you will have it also in the code, in the Python code I provide you about the animal. And we said animal fluffy, animal 4. Then we did some age different and we inherit it and we add to the inherit one. So we have all of these things, we run them, and we studied those examples. If you don't check it since last class, then those examples will not add any new information to you. You have to practice them yourself. As I told you, practice these codes I provide you in the OWL. You can find them in OWL if you see here. Here you find the practice code. And in practice code, you will find all weeks. So those are week 8 and 9. If you open it, download those files, and you can run the code in OWL tutorial. Those will show you the details, how it's going on. If you have any question or clarification, don't hesitate to send me an email or to the TA. And will be either me or her more than happy to answer your questions before the quiz. But don't send me email on Saturday or Sunday. Even Monday before the quiz, I'm more than happy to answer your question. Our quiz will start at 4. Please join at 3:55. Make sure your camera is on. I'll send an announcement tomorrow about this. Make sure that your camera is on. Okay, guys, any questions before we start with our new handout? Can you see the handout?
Yes, Professor.
Okay, so today there is no programming or a new programming concept that will be studied in this course. Handout 10 and 11, which we'll be covering tonight, is talking about program efficiency. So week 10 or handout 10, talking about efficiency 1, then handout 2, it's more details efficiency. Then the last handout will be about the sorting algorithms. So today we are measuring orders of growth of algorithm. We'll be introduced to a term called big O notation, and we'll talk about the complexity classes. How, if we want to understand the efficiency of a program, how we can do that? As we know, nowadays computers are very fast, getting faster every day. New generations are coming in a small period of time. Some may be efficient programs, don't matter. If my program is efficient or not with this speed, it doesn't matter. But when I have more program, more systems, I have to make sure that they are efficient. But data set can be very large. If we are working with machine learning, and I'm sure even whatever your specialization or your subspecialty within electrical and computer engineering. A lot of research are using AI. One of these AI aspect is applying machine learning to your problem. So if you are dealing with a data set or a very large data set, so for example, in 2014, Google served like, you know, this number, 30,000 billion pages covering 100 million gigabyte. How long to search? Brute force. Thus, simple solution may simply not scale with size in acceptable manner. How can we decide which option for a program is most efficient? So if I'm using traditional programming and not professional programming or not efficient way to deal with this program and to perform the operation required to solve the problem, then the program will be very complex and not efficient enough. So separate time and space efficiently of a program is one of the solution. Trade-off between them can sometimes pre-compute result are stored, then use lookup to retrieve, which is memoization for Fibonacci, for example, if we choose the n with large number. We'll focus on time efficiency. So normally we are looking for the complexity and the efficiency of a program to be solved with the minimal possible time to solve this problem. For example, in my PhD, I was comparing between, in one of the problems in my PhD, I was comparing between different optimization technique to optimize machine learning technique to solve the problem faster with a relatively a very, you know, it's not with this large number of records. My data set was about network security and cyber security. So it took sometimes with some algorithm 3 days to be solved, and with other efficient way of coding and efficient designed algorithms, we solve the problem with less than 2 hours. So one of the technique was taking 3 to 4 days to get the result, and the other one within 2 hours. So which one more efficient? You will say the 2 hours. But we found that some of them with 1 day to be trained to take the decision was more efficient because it was more accurate with the results. So it's not a matter of time, also the quality of output. The quality of output. Which one will give me more accurate output? So it has multiple factors we have to study, but mainly at this time, we will concentrate on time efficiency. Challenges in understanding efficiency of a solution to a computational problem. A program can be implemented in many different ways. As I told you, you can solve a problem using only a handful of different algorithms. Would like to separate choices of implementation from choices of more abstract algorithm. So you have multiple ways to solve the problem. Which one will best suit and bring the result or satisfy the objective why we designed this program for? What is the objective that we designed this program? What problem to solve? What is the acceptable level of results? Then we can put like a candidate, different way of implementation, then we can choose the best. Like we can measure them with a timer. We can count the operation. Abstract notion of order growth. We'll argue that is the most appropriate way of assessing the impact of choices of algorithm in solving a problem and in measuring the inherent difficulty in solving the problem. Now, with more advanced level, we'll talk about not only the time with running time complexity, computer resources complexity, how much it will take from the CPU capacity. If we are talking about mainframes or supercomputer, how many lines or pipelining, you know, a lot of factors, but we'll not go on these in this deep details in the complexity issue. We will stay on the surface because, guys, you are not a software engineering student that you need to know all this information. Timing a program. Use time module. You can import time library. Hash import time. Recall that importing means to bring in that class into your own file. Def C to FC return C times 9 over 5 plus 32, which is Celsius to Fahrenheit, this function. Start the clock T0 time dot clock. Call function C to F and send this Fahrenheit degree. T1 equal time clock dot minus T0, print T. So here, stop the clock. Here it will give you the time, how much time to run this code using Python, using this machine. Also the machine specs also give different because the CPU clock, if I'm applying it in like a Core i3 laptop and the Core i5 and the Core i7 with 6th generation, 7th generation, 8th generation, or 10th or 11th generation nowadays. So it will give me different time. So the time will be different by within the machine itself also, plus the algorithm. So it will give me the time difference from T0 to T1. So timing a program is inconsistent. Goal to evaluate different algorithm. Running time varies between algorithm, varies between implementation, varies between computer, as I told you, the type of computer, the type of CPU, how much RAM do you have, how cache, how many threads you have in your CPU, the bus, which is the speed of the bus, the speed of the hard disk, the speed of RAM. You know, a lot of complicated factors that could make that time is different. So time varies for different input, but cannot really express the relationship between inputs and time. So if I use like Pentium 1, old machine, that was first, I think it reduced in 1994 or 1995. 1994, I believe. So if I apply the algorithm, that machine, then I apply it in one of the latest, or I apply it in a workstation or in a server, the time will look different because the machine are different. The way I implement it, you use for, I use while, you use if statement, I use the switch, it will be different. So this time varies. That's why it's inconsistent. So what is the solution? We will find now by the end, it's the big O notation. Make a generic formula that can work with any type of computer or anything. We'll see how. The second one, they said counting the operations. Assume these steps take constant time. We'll forget about how much time we need as a whole program. We'll take the operations and we will assume that each operation will have constant time. What is it? Doesn't matter. So mathematical operation, comparison, assignment, accessing object in memory. So here in mathematical operation, we have here 3 operations, and each operation will take constant time. Then here 1 operation, which is the assignment statement. For I in range of x plus 1 loop times. In each loop we'll have one operation and two operations here. One operation in the top and two operations here. So my sum is 1 times 3x ops. Counting operation is better, but still what? Count depends on algorithm itself. Count depends on implementation, how I implement that problem, how I implement for, how I implement the loop, using for, using while. It's different. It will be different. Or count independent of computers. No clear definition of which operation to count. So by counting operation, it depends on algorithm and it independent of computers. Count varies for different input and can come up with a relationship between input and the count. Yes. Still need a better way. This is not enough to count the efficiency of the program. Timing and counting. Evaluate implementations. Timing evaluates machine. Want to evaluate algorithm, and we want to evaluate the scalability of the program, and we want to evaluate in terms of input size. If the input n, what is the complexity? If the input n squared, what is the complexity? N is an unknown number for me. Going to focus on idea of counting operation in an algorithm, but not worry about small variations in implementation, whether we take 3 or 4 primitive operations to execute the step of a loop. Going to focus on how algorithm perform when size of a problem get arbitrarily large. Want to relate time needed to complete a computation measured this way against the size of the input to the problem. Need to decide what to measure, given the actual number of steps may depend on the specific of trial. Need to choose which input to use to evaluate a function. We want to express efficiency in terms of size of input. So if we want to express the efficiency in terms of size of input, so I need to decide what is your input. Could be an integer, could be length of a list. You decide. When multiple parameters to a function. Search for element L and E. So as I told you, multiple factor we have to take in our consideration. How we want to evaluate, how we can say this program is efficient or implementation A is more efficient than implementation B. How to reach to that point that we can decide that this implementation is better than that implementation. Multiple factor we have to take in our consideration. A function that searches for an element in a list. So if we define a search for element L and E for I in L, if I equal E, return true, else return false. When E is first element in the list, we call it best case scenario. So we run it one time and done. When E is not in the list, which is worst case scenario, I have to check every single element in that list, and at the end I'll not find element E in that list. And what about if the element E is at the middle of the list? We call it average case. Want to measure this behavior in general way. I cannot say if I find it the first element in the list, oh, it take one round, efficient. If it is not in the list, or it is an average, how we can generalize the rule of efficiency? Best, average, worst case. We have these possible, or in between best and average, between average and worst. How we can evaluate this? Suppose you are given a list L of some length L, len of L, best case minimum running time over all possible input, as I said, of a given search for element, first element in a in that list. Average case, it's in the middle. Worst case, maximum running time over all possible input of a given len-al, linear in length of a list search for element, must search entire list and not find it, which is the worst case scenario. Normally, we will focus in which one? In the worst case, which is the maximum possible time that I might take. Orders of growth. Want to evaluate program efficiency when input is very big. Want to express the growth of program running time as input size grows. More input, then more running time we need. Want to put an upper bound on growth as tight as possible. Do not need to be precise. Order of not exact growth. We will look at the largest factor in runtime, which section of the program will take the longest to run. Thus, generally, we want tight upper bound on growth as function of size of input in worst case scenario. So we are combining, so those the thing that we are looking all together. So we define a term, we call it big O notation. Big O notation. Big O notation measures an upper bound on the asymptotic growth, often called order of a growth. So what is big O? It's the order of a growth. Of what? The upper bound on a growth, which is the maximum, which is the worst case scenario, and with the maximum possible size of input. So this is the big O. Big O, between brackets, we'll have something here, is used to describe worst case. Worst occur often and is the bottleneck when a program runs. Express rate of growth of a program relative to the input size. Evaluate algorithm, not machine or implementation. So we are evaluating the algorithm itself, not the machine or the whole implementation. Example, steps versus big O. So fact of an answer equal 1, while n greater than 1 answer equal answers times n equal n minus 1, return answer. Computes factorial. This algorithm, we took it before that, computes the factorial of any given n number. Number of steps. If we found it, it's 1 plus 5n plus 1. Worst case asymptotic complexity, it's a big O of n. So we'll take the maximum number or the worst case or the upper bound, which is n times. We will forget about constant. So it's big O of n. Ignore additive constant, ignore multiplicative constant, all plus or times. Normally we just take if there is a power. Don't forget, like we have O to n square, O of n square, but we don't have O of 2n. We'll make it back to O to big O of n times. What does O of n measures? Interested in describing how amount of time needed grows as the size of input to the problem grows. Thus, given an expression for the number of operations needed to compute an algorithm, want to know asymptotic behavior as size of problem gets larger. Hence, we'll focus on term that grows mostly rapidly in a sum of terms, and will ignore the multiplicative constant since want to know how rapidly timer required increases as increase of the size or as the increase of size of input. So we drop constant and we drop multiplicative. So like if we have n squared plus 2n plus 2, it's big O to n squared. We have n squared 10,000 or 100,000 n plus 3 to the power 1,000, then it will be big O to n squared. Log n plus 4, it will be big O to n. If we have n log n, see here, if we have n log n, we'll take n log n. 2 to n to the power 30 plus 3 to the power n. Which one? We'll take 3 to the power n. So, types of growth: constant, linear, quadratic, logarithmic, and log n, exponential. So normally we said this program complexity having exponential growth, which has or n log n, or logarithmic, or linear complexity, or constant complexity, or quadratic complexity. Combined complexity class. How we analyze programs and their complexity. So we combine complexity classes, analyze the statement inside the function, apply some rules, focus on the dominant term. Law of addition for big O. Use with sequential statement. Big O of f of n plus big O of g of n is big O of f of n plus g of n. For example, for I in range of n, print A, which is big O of n. For j in range of n times n, print B. So it will be big O of n plus big O of n times n. Is big O of n plus big O of n times n, which is big O of n plus n squared. It will be big O of n squared because of dominant term. So the dominant term will form the big O final term. Clear, guys? So for example, for I in range of n, for j in range of n, print A, O big O of n, then n loop, each loop O of n times O of n. So it will be O of n times of O n, and here it will be big O of n squared, because the outer loop goes n times and the inner loop go n times for every outer loop. So it will be big O of n squared for nested loop. So in nested loop, we take the out term plus the times the inner term, and it will form big O of n squared. Complexity classes. Big O of 1 denotes constant running time. O log n, it will give me logarithmic time. O of n, linear running time. O of n log n denote log linear running time. O of n to the times c, polynomial running time. C is a constant. Big O of c to the power n denote exponential running time. Okay, guys? Here again. How it's constant, how it's logarithmic, linear, log linear, polynomial, exponential. So big O of 1, if n equal 10, it's 1, 100,000, it's 1. O log n, if n equal 10, it's 1. If n equal 100, it's 2. 1,000, 3, million, 6. O of n, it's 10, 100,000, million. And log n, it's 10, 200, 3,000, 6 million. O to n square, that time. O to the power n, good luck to count it with million. Okay, guys, it will be very complex. Simple iterative loop algorithm are typically linear in complexity. For example, if I have one for loop, it's big O to n. Constant time, list access. So if I wanna to access like the ith element, so I will count the base plus the ith element. If the list heterogeneous in direction references to the other object, so we'll have a linked list. Linear search in sorted list. This is a linear search algorithm for I in range of length. If L of I equal E, return true. If Li return false, return false. Must only look until reach a number greater than E. O ln of L for the loop O of 1 to test if E in L of I. Overall complexity is big O of N, where N is the length of the list. Note, order of growth is the same, through running time may differ for two search methods. This is for linear search. If I use like binary search, it will be different. So big O to ln S with linear complexity. Again, linear complexity, big O of N. Even if I have here 1 plus 3, N plus 1, no, it will be big O of N because this is the dominant pair. Nested loop, simple loop are linear in complexity. What about loops that have loops within them? Nested loop. I have here for I in L1, for E2 in L2, I have two loops. What will happen? We call it a quadratic complexity. So big O of ln L1 times ln of L2. Then worst case, when L1 and L2 same length, none of elements of L1 in L2. So we'll take big O of ln of L1 square. This is the worst case scenario. Again, the same thing to compound. Big O for nested loops. If it's the same, and it will be big O of n square as we described before. This time and next time. We have example of loop and nested loops. Give rise to linear and the quadratic complexity algorithm. Next time, we'll more carefully examine examples from each of the different complexity classes. So it will be more detailed examples the next handout. So would you like to have a break or shall we continue? Questions? Hi, guys. Question or a break?
Break.
Okay, let's have like 10 minutes break and we'll back at 5:10. I'll pause the recording and we'll back at 5:10. Okay, guys, we'll come back. We will continue with the next part of our topic today, which is the program efficiency part 2. We covered in the first part of this lecture about big O notation and the complexity of loops and nested loops. Now we'll talk about the classes of complexity. We talked about it last class or or in the first part of our class, and we will have some example characteristic of each class. So why we want to understand efficiency of program? How can we reason about an algorithm in order to predict the amount of time it will need to solve a problem of a particular input size? How can we relate choices in algorithm design to the time efficiency of the resulting algorithm? Are there fundamental limits on the amount of time we will need to solve a particular problem? To answer these questions, we define what we call it orders of growth. To recap what we talk about, it was we want to evaluate the efficiency when input size is very big. We want to express the growth of program running time as input size grow. We want to put an upper bound on a growth as tight as possible. Do not need to be precise, order of not exact growth. We will look at largest factor in runtime, which section of the program will take the longest time to run. So the program is consist of some sections, some section will not take that amount of time. So we are looking about the largest one. Thus, generally, we want to tight upper bound in a growth as function size of input in worst case scenario. So this is what we are trying to do. This is what we are trying to do. So we talk about different type of complexity classes. We start with constant running time or logarithmic running time or linear running time or log linear running time or polynomial running time or exponential running time, which is the biggest. And here again, we have the same figures that we discussed at the first pass of that. So big O of 1, it's a constant. Big O of log n, with the larger amount of input, it will have larger or more complexity. Big O of n, it will be linearly increase with the size of input. Here it will go in a logarithmic or log linear with the size of input. Here it will go in a polynomial. And here we'll go exponential depending on the size of input. And the same slide is repeated. Constant complexity independent of input. Whatever the size of input, it will be constant. Very few interesting algorithm in this class, but can often have a piece that fit this class. Can have loops or recursive call, but only if number of iteration or call independent of the size of the input. So the number of calls is independent. The size of input will not affect the number of calls or of iteration in these programs. Logarithmic complexity grows as log of size of one of its input. Example, bisection search or binary search, which will be introduced in next class after the quiz, the binary search. Bisection search, suppose we want to know if a particular element is present in a list. So last time that we could just walk down the list, checking each element with linear search, but with bisection, complexity was linear in length of the list. Suppose we know that the list is ordered from smallest to largest. If I have order list and I have a certain element I want to look at, so that the sequential search was still linear in complexity, can we do better if it's ordered? Yes. If the number I am looking is greater than the middle of the list, then I can search in the second half of the list. No need to search the whole list. So here we can like have a better performance and fewer time to find if the element is in the list or not. So how we do that? We pick an index I that divide list in half, ask if Li is equal the middle element. If not, we will ask if Li is larger or smaller than E. Depending on the answer, search left or right of the E, which is a new version of divide and conquer algorithm, break into smaller version of problem, smaller list plus some simple operations. Answer to smaller version is answer to original problem. At the end point, we want to know if E is in the list or not. This is the answer I'm looking for. So how it will be, we have an element, finish looking through the list when n divided by 2. So I log n, complexity, it will be big O to log n, where n is the length of L. So here we divide it into smaller pieces. This is the implementation of section search. At the beginning, if L empty, return false. We have an empty list. Else, if L equal 1, return L0 equal E, which is constant of 1. Else, if len of L divided by 2, if L half greater than E, then we'll go to the we'll search in one direction. If it's a greater, or if it's smaller, we'll go to the other direction, to the left. If it's greater, we'll go to the right. So it's big O log n bisection search calls all of these operation. It will be n log n again. Turns out that total cost to copy is big O of n, and this demonstrates the log n cost due to the recursive calls. What is the alternative? We divide it into half. Then if we find it's less than this media, we'll divide again, this is into half. Then we can search and divide it into half again till we reach to the element. And here it will be big O to log n. So this is the other implementation, which is implementation 2. At the end point, we'll end that the bisection search will have a complexity of big O of log n again. Logarithmic complexity. So if we define the digit from 0 to 9, if I equals 0, return 0, result equal nothing, while I greater than 0, result digits divided by 10 plus result, I, the modular of 10, return the results. Only have to look at loop, no functions call. Within while loop, constant number of step, how many times through the loop? Now, how many times can one divide I by 10? So it will be big O log I. So this last time, searching a list in a sequence to see if an element is present, iterative loops. This one, the same example, and it will give big O to n. We discussed it at the first part of lecture, which is in the previous handout. If we have a recursive factorial, if we do a recursive function to do the factorial, how much it will be? It depends on the size of n. So it will call n times uncertain times. So when we say n times constant, we'll eliminate the constant. So it will still big O of n. So iterative, if I'm using 4 to find the factorial, or recursive, has the same order of growth. They have the same complexity. Log linear, many practical algorithms are log linear. Very commonly used log linear algorithm is merge sort. There is a merge sort. If you are interested for the merge sort, we'll have it next lecture, and we will return to this next lecture. Polynomial complexity. Most common polynomial algorithms are quadratic. Complexity grows with the square of size of input. If I have input of n, it will grow by n squared. Commonly occurs when we have nested loop or recursive functions calls. Like sometimes we have a nested recursive functions. And last time we saw the recursive. Exponential. Recursive function where more than one recursive call for each size of a problem. Like towers of Hanoi, we have a double recursive. Many important problems are inherently exponential. Unfortunate. Many important problems are inherently exponential. Unfortunate as cost can be high. So with exponential, the cost is high, the running time is high with the growth of the input size. will lead us to consider approximate solution, as many provide reasonable answer more quickly. So this is the complexity of tower of Hanoi. Let T of n denote time to solve tower of size n. So we have 2T n minus 1 plus 1, etc. So it will be the order of growth is O2, 2 to the power n. So as the input size is growing with the growth, so it will be a more complex problem. So 2 to the power 4 if we have 4 inputs, but if we have like the size of n is like 1,000,000, so it will be 2 to the power million. So it will be very expensive. We call it very expensive in computer science. And the orders doesn't matter. Power set concept. We want to generate the power set of integers from 1 to n. Assume we can generate a power set of integers from 1 to n minus 1. Then all of those subsets belong to the bigger power set, choosing not include n, and all of those subsets within n add to each other, like 1, 2, 1, 2, 3, 1, 3, 2, 3, 1, 2, 3, 4, and etc. So nice recursive description. So it will be multiple recursive inside each other. So this is the implementation of exponential complexity. Assuming append is constant time. Here, this append has a constant time. So time includes time to solve a smaller problem plus time need to make a copy of the all element in smaller problem. But important to think about the size of smaller. Know that for a set of size k, there are 2 to the power k cases. How can we deduct or minimize the overall complexity? And with this one, it's 2 to the power still. Thus, computing power is set to big O to the 2 to the power n, which is very expensive, complex. We call it complex problem. Again, we go back to these complexity classes. Iterative Fibonacci, worst case, it will be big O of n, as it's here counted, and here we'll have linear big O of n, and we, as we said, we take the dominant term. So if we make it recursively, the Fibonacci sequence, it will be big O to 2 to the power n, which is the worst case. So here, iterative, which will be more efficient. Recursively, it will be more complex. So compare efficiency of algorithm, the big O. Notation that describe growth, lower order of growth is better, independent of machine or specific implementation. If you see here, we talk about the complexity of the algorithm, the efficiency of the algorithm itself, whatever which machine we are, and whatever the size of input. So we use big O, describe order of growth, asymptotic notation, upper bound, and we study with big O the worst case scenario. Like complexity of common Python function that we use it. List n is len L, index big O of 1, store, length, append, equal, remove, copy, reverse, iteration, in list, dictionaries, worst case, index big O to unstore, length, delete, iteration, average case, index big O to 1, whatever. So these are some common complexity that we know within Python function that we studied till the moment. Questions? Questions, guys?
First, I have a question.
Yes.
For example, for the bisection set,
Yes.
If we're doing the bisection search, doesn't the list have to be sorted?
Yes,
for
we
it to
said
work?
that. Yes. Yeah, we said that.
Then won't the sorting, when they're sorting out the
Yeah,
complexity,
that
like
would
priority
that would
seems to
that
add
would be that would be depending on the sorting algorithm that we use, because each sorting algorithm also it has its own complexity. And as we mentioned from the beginning of the this lecture, we said that if we'll take the largest big O between different algorithm or between different program sections. So for example, if we are doing a sort, like if we use the bubble sort, which is I think big O of n, and we use the bisection search, which is big O of n log n. So the complexity of bisection search is larger than bubble sort. So we took normally, as we told you, the most dominant variable of big O. For example, if I use bubble sort and linear search and bisection search in the same program, each has its own complexity. When I ask you about what is the complexity of this piece of code, you will choose the largest one, which is the bisection search. Because we don't, as we said, it's not the exact. It's the maximum growth. Is that clear?
Yes, it's clear.
Yeah.
Thank you.
You are welcome. Any other questions, guys? If you don't have a question, you can leave. You are free to leave. We are done. See you next Monday at 3:55 to start our quiz. And I will upload the video by tonight. I hope that I can do it by tonight. I'll stop recording here and see you next week.